you know, this is not going to, we don't have that in CNN, we don't have that in MLP. So in the MLP, okay, when you train a layer, say, if you, of course, CNN or MLP, it's going to be like, you know, we don't have unrolled through time. So actually, when you train a layer, okay, something like this, of course, they represent different weights, right? Each layer has different weights. But now, okay, all these have the same weight. So that's the primary difference. Okay, the primary difference. So, okay, the same weights are used at every time step. Okay, so the output at the second time step may also be slightly increased, and so and the third step, and so third time step, and so on. So eventually, okay, the output until the output explodes. Okay, so because when we say non-saturated, I'm talking about, you know reloads like this, right? Right? So you, this value can go very big, right? This value can go very big. The result of the reload activation function can be very big, right? After you apply reload, it could be very big. But on the other hand, the saturating activation function, okay, such as hypertension, okay, the result is in between -1 to +1, right? Okay, so it is bounded, right? Yeah, we have the saturating function. The issue is like the gradient is going to be very small. Yeah, we have that issue as well. But at least like the output is not going to be, like unbounded. Okay, so the saturating function, such as like hypertension, okay, does not have that issue, does not have that risk. Okay, so that is why, okay, the hypertension in the RNN is normally used as the default, Okay, I'm not saying reload can never be used, but I'm just saying, in RNN, reload is not as popular as hypertension. Okay, not as popular. Of course, you can say, how about gradient? Because saturation function have that vanishing gradient issue, right? But as I said, like in RNN, most of the issue comes. When we say in the RNN, the unstable gradient, what the unstable gradient in RNN actually normally refer to exploding gradient, because like it somehow like especially in long sequence training, okay, either gradient or like the result function gets enlarged and enlarged. Okay, eventually explode. Okay, but for saturating function, if you have that vanishing gradient problem, we already know a lot of technique to fight with that. We already know a lot of techniques. Okay, especially the ones that we learned from the chapter 11. They are still okay. Okay, another way. Okay, the gradient, let's say, okay, explode too. Okay, so if you notice that training is unstable, most of the case is because of the exploding gradient. Okay, so you may want to monitor the size of the gradient. Okay, and how do we monitor the size of gradient? We talk about TensorBoard, right? TensorBoard is able to allows you to monitor the gradient, like during training. Okay, and if that happens, you can also use gradient clipping. We talk about gradient clipping in chapter 11, right? Okay, which help you to prevent gradient, exploding gradient as well. Okay. So, yeah, and remember, like in chapter 11, I mentioned like batch normalization is important technique, right? I mean, this is so important that in chapter 12, when we talk about CMN, you see batch normalization. Is always used like right after the convolutional layer. Okay. How about in yes, we can still use batch normalization, but there's some research that they found out that BN was slightly beneficial only when it was applied to the input, not to the hidden layer, hidden state. Okay, so because if you try to apply batch normalization directly, then it will apply to both the input and the hidden state, because hidden state is also considered, that's the feedback, remember? That's also considered as the input of the neuron, okay? So in other words, okay, it's slightly better than nothing when applied between recurrent layers, okay? But not within recurrent layer, okay? So, so basically, okay, in Keras, okay, this can be done by adding a batch normalization layer before each recurrent layer. But the issue is, the batch normalization, you cannot expect the BM help you a lot. It's not like convolutional neural network or the other cases like BM help a lot. Okay, instead, if you say batch normalization doesn't help that much, what else? What other option do we have? Okay, there's a concept called layer normalization. Okay, which was proposed in a 2016 paper. Okay, this concept, is similar to batch normalization, but instead of normalizing across batch dimension, it normalizes across feature dimension. Okay, so it normalizes your features. Okay, based on different features. Okay, so the advantage of this is that it can compute the required statistics on the fly at each time step. So you don't need to remember in the batch normalization. If you still remember our discussion, in chapter 11, you will know that batch normalization during training and during inference act differently. Remember? Because during training, you have the batch, right? So you get those statistics from each batch easily. But during inference, because you may not have that batch concept, right? So you actually have to, estimate those statistics, okay, from during the mini batch, from the mini batch training process, okay, and use that in the inference. But the layer normalization, okay, it remains the same, okay, regardless it's you are doing training or you are doing inference, okay, so it's a much easier, process, okay. So normalization will learn, scale, and offset parameter for each input, okay, directly. And in RNA, it is typically used right after linear combination and before and the hidden state, and before the activation function is applied. So, so we can, we can implement like a layer of normalization in Keras, okay, with a simple memory cell, okay. So this is an example, okay. Class layer normalization simple RNN cell, okay. It is a subclass the layer, okay. And here, okay, these are pretty much, very very easy, okay. So we don't need to change that much. The only thing we add is here. We create this Keras.layers, layer normalization. Okay, but remember, we don't specify their relationship. Like in here, we specify their relation actually in the call method. So here, okay, you can see that, okay, we first compute the output, okay, first. And then, okay, we apply the layer normalization to this output. Okay, oh, by the way, the output and new states, they are the same, because it's a simple RNN cell. We know that, right? And the output and the state are the same. So then we apply the layer normalization first before we apply the activation function. Okay? And then we just output the same thing twice. The first one is used as an output. The second one is used as like a state. The state is actually a list because, in general, the RNN cell can have more than one state. Okay, so that is why it is like a list instead of just one value. Okay? So, yeah, I think I already explained like what this code is. So, yeah, not much to explain here. And then you can use this LN simple RNN cell to create a model like this. Model, okay, still use sequential API. So in the layers RNN, okay, you use the LNS simple RNN cell, okay, to create like 20 this. Yeah, this is a simple RNN cell. Yeah, this is simple RNN cell, and we use that to create a simple RNN cell with the layer normalization. Okay, we have 20 simple RNN cell with the layer normalization, and the other parts remains the same. Okay, we apply this LN simple RNN cell. Okay, and the other part. So up to now, okay, this is like one technique you could use, okay, to improve the training and the fight with the exploding gradient in RNN. Okay, so let's take 10 minutes break. When we come back, we will continue our discussion on the other technique that help you to train RNN.